Yeah, so we are working on the same project, two sides of the same project. Going to talk about astronomy, not actual hierarchical Bayesian networks. At least I'm not going to go into astronomy. It's more interesting. It doesn't work. So the project I'm working on with my colleagues at Johns Hopkins is a Japanese project. It's a new spectrograph for the Subaru Telescope, which is situated in Hawaii on the Mauna Kea. And the one on the left is the Subaru Telescope. It's an 8.2 meter telescope. And now an international team is building this so-called prime focus spectrograph for this telescope. And it will be able to do low and medium resolution spectroscopy from the infrared, near infrared, to the visible blue light of the electromagnetic spectrum. One is that it has a large mirror, so it's an 8-meter class telescope. There's only a handful of those around the world. And it also has, and this makes it unique, a large field of view. So we see a significant part of the sky, about 3 times the diameter of the full moon when we use this telescope. So this makes this instrument very unique for those observations that we are planning to do. I want to talk about that. So this is the Subaru Telescope. This is huge. So the mirror diameter is 8.2 meters. So this whole structure from bottom to top is about 20 meters. It's large. And the prime focus spectrograph goes up here. So this is the prime focus of the telescope. Here's the mirror down here. So this whole instrument goes on the top, and it's going to be consisting of these fiber positioners. So the way it works is that the light gets reflected from the mirror, it gets to the fibers will be terminated up here with these fiber positioner mechanics. So we will be able to automatically position the fibers to the objects we are interested in. So within a petrol radius of each fiber, we will be able to choose which star or which galaxy to observe. And this whole thing can be reconfigured to different objects in about a minute. So while we are doing observations and we decide to move on from one object to the other, it will be possible without basically taking the whole telescope apart. And this will have lots of advantages. And actually, this is where most large room for optimizing the observations. And if there's a large room for optimization, then machine learning always comes in. So this is the frame that will hold these fiber positioners in a hexagonal setting. It's going to be pretty large. And this is one of the cameras. Again, this is in the lab. And I saw this myself, and it's about this big. So this is just one of the cameras, and there will be 12 of these. It's currently being built in Baltimore and Johns Hopkins. And there in parallel at the same time.
What does it mean to position these things?
So yeah, so you take an image of the sky, right? We already have those images, and then you find the objects that you want to observe. Actually, this is what I'm going to talk about. So what are the objects and how where you want to position your fibers.
But the fibers are fixed?
No, the fibers move around on these positioners. Okay, so you can position a fiber on any of the objects you want within the fiber radius. And you have 2,400 fibers to allocate over the object. And then we do observations in 15-minute increments. Okay, so the project that we are working on is called Galactic Archaeology. So we are looking for very old things with the intention of understanding how stars. We are going to observe the local universe, so not distant galaxies as other sky surveys do, but we are interested in individual stars. So we will try to find and observe spectra of stars in galaxies other than the Milky Way. And these will be satellite dwarf galaxies orbiting the Milky Way, and also the Andromeda galaxy. So that's close enough that we can see the individual stars, only the brightest stars, but we'll be able to observe those. So we are interested in the formation history of the Milky Way. And for instance, we'll be able to observe, if you look at the background, it's a little bit dim, but here's the Milky Way, and there are satellite galaxies orbiting the Milky Way. And when they gravitationally interact with the disk of the Milky Way, beams are formed of those very, very old metal poor stars that the satellite galaxies are composed of. So when we observe these and the exact kinematics of these stars, then we can reconstruct the dark matter distribution within the Milky Way. Okay, so just a few basic things we can observe. So when we do imaging, photometry, we see the apparent bright. Very high resolution, then we can always measure the 2D position of a star on the sky. If we have high resolution, we can measure the 2D velocity of these stars. And some satellites can also measure distance, but we are not relying on those because we are looking for faraway stars. And this is not enough to do galactic archaeology. To do galactic archaeology, one needs spectroscopy, because we also want more precise temperatures. We want the so-called gravity. So gravity is the gravitational acceleration at the surface of the star, whatever the surface is. It's not a solid surface, of course. How dense the star in the photosphere. And this is to tell red giants from red dwarfs. I will explain briefly what these are. Okay, we can measure the metal content, and the other important quantity to measure to reconstruct the kinematics of these stars and their interaction with the Milky Way and the dark matter distribution is radial velocity. It's called radial velocity because it's the line of sight velocity. And we can measure it from Doppler shifting of the spectral lines. So this is what we are shooting for. And of course, we will need to skip these, it's not that important. So this is how a red giant like our sun, or even smaller mass, lower mass star, which is even redder than the sun. And red giants are stars which are very voluminous. So they are large in size, but not necessarily in mass. Okay, they are so-called evolved stars. So if we look at theory and we have some estimate of their sizes, then we see that the red dwarf is about this big, and then the red giant is this big. So it's much brighter. It produces a lot more energy, but it has the same temperature, surface temperature. Of course, they have very similar mass. It's just that the red giant is a little bit older than a red dwarf. But if we look at these through the telescope, and the red giant is in a satellite galaxy 100 kiloparsecs away, which is don't even know how many light years, but outside the Milky Way galaxy, and the red dwarf is within the Milky Way galaxy, somewhere in the vicinity of the solar system, then they will appear exactly the same in the photos. Okay, so if we want to pick which one to take a spectrum from, it's a challenge. Okay, this is where Bayesian networks will come in, because we can tell all kinds of probabilities of being a red giant or a red dwarf. Okay, I'm going to skip this too. So this is how we tell from spectra which dwarfs have a dense atmosphere. So the spectral lines are broader due to broadening from pressure. Okay, if it's a red giant, the red giants have very low pressure atmospheres. So the absorption lines will be much thinner, narrower. To pick which star is which from photometry only.
And the content is always the same or different?
It's usually different, but you can't really disentangle it from the age if you just look at photometry. There's a degeneracy that you can only resolve with spectroscopy, or also narrowband filters, but I'm not going to talk about that. Now, this is how a dwarf spheroidal galaxy looks like. It's one of the satellites of the Milky Way. It's the Sculptor galaxy. As you can see, it's a slight overdensity on the sky. So you can clearly there's something here, because the density of the stars is larger here than here. But if I show you a tiny orange dot, can you tell whether it's a red dwarf or a red giant? No. Okay, it can be in the foreground, or it can be a member of the satellite galaxy with some probability. Of course, the probability is higher here in the middle, because the satellite galaxy is denser. Probability of membership, but the probability of membership here is much lower. But being members or being foreground stars, then we have to decide which ones are interesting enough for a spectroscopic observation and how much failure rate we can accept. Because sometimes we will put a fiber on a star and it's going to turn out as a foreground dwarf that we are not. These large telescopes. So we want to optimize the observations. So this is how astronomers look at the images. Okay, so what I'm showing here is a graphicon or calculated from the brightness measurements of two different difference of the brightnesses, or the ratio of the brightnesses. This is what we get if we analyze the images of a satellite galaxy. And what you can see here is that the color is roughly the equivalent of the temperature, and this is the brightness. So the brighter stars are toward the top. And interestingly, these stars, which draw this nice track on this color magnitude diagram, are all members of the dwarf satellite galaxy. And that's because these stars are all at the same distance. Okay, so they follow, their brightness follows the theory nicely. All the stars that are scattered vertically are members of the Milky Way, and they are at very different distances. So they just nicely fill up the foreground on this color magnitude diagram. Now this track here is called the red giant branch, and these stars are all red giants. And then everything else is just different components of the Milky Way. which have a very distinct distance distribution. Okay, we don't care about those. We want to target these stars. But of course, this red giant branch, which we stars, and we want to get rid of. If we look at the theory of sterile evolution, if someone tells me what the metal content, the initial metal content of a star, its mass at formation, and the current age of the star, then I can tell how bright it is in the different color filters. And these results are calculated and tabulated in so-called isochrone tables. Okay, so I need to interpolate these isochrone tables, and then for any combination of these physical parameters, I can calculate the magnitudes of the star in any filter system that we have. Now, what if I want to do it the other way around? So I observe a star, I know its magnitudes in each of the filters. How can I tell the physical parameters? I have to invert these, but these functions which convert the physical parameters in valued sometimes, and it's just very messy. Okay, so inverting these is in itself a problem which can be solved with Monte Carlo methods. But we will go a step further, and we want to stellar populations that we see. So what are those stellar populations? One stellar population will be the members of the satellite galaxy, and then different populations of the Milky Way, like these are the Milky Way disk stars. This part here, the blue part, is the Milky Way halo. So these will be the populations that we take into account. Now we have to make more assumptions, and we are going toward the Bayesian model because we'll talk about priors here. So we know quite a lot about the Milky Way. So we know that it consists of different stellar populations, like the disk and the halo. Distribution of these components. Okay, so usually the density of the stars decreases exponentially as we go further out from the center of the Milky Way. Now we also know about the metal content distribution of these stars, and so on and so on, also their kinematics. Mass function of the stars. So the mass function basically tells when stars are formed in a gas cloud, they are formed with different masses, and we know this distribution of the masses. This is very important for this whole Bayesian analysis to work. Okay, and we also know that the dwarf galaxy member stars are at the same distance. They are very far. And we have to fold these in. And this is where we can build our Bayesian mixture model. I'm not going to write formally, but basically we have to calculate the posterior probability for each of these stars being members or being non-members, where membership means member of the dwarf galaxy. And this turns out to be a mixture model in Bayesian statistics, which is a little bit tricky. And it poses lots of challenges. Of course, it's computationally intensive. That's going to be one of the challenges, but there are mathematical challenges that we haven't really solved yet fully, because it involves sampling categorical variables, so non-continuous variables. That's the membership star. And okay, so how do we construct this Bayesian model? We have some rough assumptions on the on the weights of the populations. We have priors for each of the physical parameters of every star. So what's the distribution of the mass, what's the distribution of the age, the metal content, and so on and so on. And for each population, we have these distributions as assumptions. And of course, we want to fit Milky Way. We know most of these parameters, so we can just plug those into the model. But for the dwarf galaxy, we want to fit the mean age of the stars in the dwarf galaxy, or the Bayesian models can do this. What they can't easily do, or not well documented how it should be done, is when we mix populations together and then we want to get the population memberships. Okay, so we also fit the population parameters, as I mentioned, but as a byproduct to all of this, for each and every star, we will have the posterior distribution of all the physical parameters. So we'll be able to tell for each star that, assuming it is a member of the Milky Way, its mass is a little bit higher, okay, or its age is a little bit older. And we can do this for 100,000 stars in parallel. And we have to do this for 100,000 stars in parallel. So just imagine it. So when we are solving this Bayesian mixture model, it's like a Monte Carlo on a million variables in parallel. So this is basically the problem we are trying to solve. Of course, it's a tricky Monte Carlo because it's interleaved. So the individual stellar parameters need to be stepped or evolved in every step. And then we have to switch to the population parameters, and then we step the categorical membership variables. So it's within a Gibbs sampler. So it's a tricky hybrid Monte Carlo sampler that we had to put together. Because talked about that distributions that we know, but none of those distributions can be easily described analytically. So we have everything tabulated. And this is, because of this, it's very computationally intensive. And this is unfortunate toward analytic problems. So we couldn't really reuse those. We had to rewrite everything basically from scratch. Not Monte Carlo sampler, but unfortunately those didn't work. Okay, so we have three types of numerical problems that we have to solve on a large scale at every step. Of course, we have linear algebra, small matrices, but 100,000 of those. We need to be able to very quickly randomly sample variables for all kinds of distributions. Some of these distributions are tabulated, and we want to avoid rejection sampling at all costs, because that's very pricey. And we need to do isochrone table interpolation. That's a pretty convoluted iterative method. So it's not a linear interpolation. It's a lot more than that. And so once we get the memberships, we will get plots something like this. And this is a logarithmic plot. So the red is high probability members. White is around 10% probability of being a member, and then blue is non-members. And these are the stars that we want to target. And actually, it's an interesting problem. If I have a minute, I will try to explain this, because we want to find the stars which are members, but that's not enough. because we want to optimize this whole targeting algorithm to answer scientific questions. So we want to target stars which are very likely members, which are bright enough to measure the physical properties from the sun. We also want to optimize for a subset of stars that can help us answer questions like what is the distribution of the dark matter in a satellite galaxy. Okay, these are hard optimization problems. We don't optimize. Choose which subset of the stars to observe together in order to answer the scientific questions. So we optimize for the scientific gain, and we are willing to take risks. So we will observe stars which are only 10%, which have only 10% membership probability. But if we succeed, star, it will just bump the utility of our observations a lot, because we will be more likely to answer the scientific question at the end. Okay, so and let me stop here because a little bit about the implementation details. So this whole thing is implemented in TensorFlow, but we use eager mode. So TensorFlow is originally for deep learning. There's no deep learning here. And because none of our distributions are actually analytic, we can't even benefit from the fancy features of TensorFlow, like automatic differentiation. We don't use that. But it's still a nice programming environment for the GPU. The other one being PyTorch. For some reason, I ended up using TensorFlow. Of the execution into execution graphs instead of running in eager mode. So it would be a little bit faster, not significantly. And we had to implement this adaptive Monte Carlo sampler from scratch, but we could rely on high-level probability package, which has a very nice tool set for generating random numbers, for example. And it requires a pretty big card, because we are running it on Tesla V100s with 12 gigabytes of RAM. About half of the RAM is used for solving one of these problems. And one of my current problems is that eager TensorFlow doesn't support multiple GPUs at the same time, which would be great, but that's not available at the moment. So we are waiting for that. And I'm leaving this slide here, and I'm happy to take questions.
Thank you very much, Laci. So you mentioned the beginning the distribution, so the mass distribution of the stars.
Yes.
And and also so how it distributed within a galaxy. And
yes.
Do you and in the very beginning you mentioned also that this can be some relation to estimated dark matter or dark matter mainly. So what is the relation for this Bayesian selection if you would miss the mass distribution of the star?
The mass distribution, it has no relation to the dark matter. At least we think it's universal. So the initial mass function, as it is called, is the now wherever we look, it appears to be the same. So where we can connect this to the dark matter is the motion of the stars, because the dark matter basically controls the motion of these stars. The Doppler shifts, basically, that's what tells us what the underlying dark matter distribution is.
Okay,
So that's why we have to optimize for a
and there's
set
no
of
effect
stars.
of this on the Bayesian and the selection document?
Well, you can do it at many levels, but of course it can have.
Yeah.
It can have. So at the end, when you optimize the observations, that's why maybe Alex will talk about this tomorrow at the workshop.
Mhm.
But so the dark matter halo profile at the end, then you have to target specific stars, and that's where you have to take risk to observe stars which are likely non-members, but you need those stars in order to constrain your model.
Yeah.
Okay, so this is where it becomes a hard optimization problem.
That partly answered my question. You said that you are optimizing for scientific value, and that's a vague problem. And you said that the properties you're interested in is whether it is member of the population and whether it is bright enough to actually see something of it. Are these the only two? Or
so what you call the vague is that, just imagine this. I have these stars, I know the membership probability. Okay, so this is just step is we have the probabilities, but we also have a model that we want to fit to the data. Okay, and we want to observe stars with the constraint of knowing the membership probabilities so that we can fit our model. This model fitting is another tricky Monte Carlo code that we want to run.
That becomes a tessellation problem with some weighted value, not just overlapping, but some other weights.
It becomes a difficult problem. And then there's the problem of assigning the fibers, which is another. So there are these very tricky optimization problems.
Final question. So do you have a standard candle like
Standard, yeah, because the tip of the red giant branch. Okay, so the brightest red giants can be considered pretty stable standard candles.
Oh,
yeah.
okay.
So you can use, if you find them.
So that has the 100% probability.
100% probability will be unlikely. Okay. The probability of the probability will be low.
Okay.
All right. Thank you.
So thank you very much, László. It was a very nice talk.